Right, grade 10s, welcome to this lesson. What we're looking at is something called kinematics. Right? When we talk about kinematics, we're looking at things like motion or movement. And if I'm looking at motion or movement, then I must look at two other concepts. I must look at speed and I must look at distance, right? And I must look at something called acceleration. Right, now, when we do this topic, we're looking at mechanics. And in this section, I cannot emphasize how important it is for us to practice. Right, so we're basically looking at situations where we have cars moving or people moving, right? And we need to analyze what do we mean by that type of movement, right? So there's two parts to this section. The key concepts. The first one is something called vectors and scalars. And the second topic that we have is called motion in one dimension. And what we mean by motion in one dimension, if I had an axis like this, I have two dimensions. One dimension is horizontal and the other one is vertical. So at grade 10, we look at motion that's either vertical or motion that's either horizontal. So we're working in only one dimension at a time. We're not working with something that's moving vertically and horizontally at the same time. We're either looking at something that's moving along the x-axis, horizontal to the earth, or we're looking at something that's moving vertically, which is going to be perpendicular to the earth. So those are your two key concepts. Let's have a look at the first one. Let's rule a line here. Right, the first thing we're looking at is different types of quantities. Now let's have a look at the two types of quantities. So the first type of quantity that we have, let's do a little table like this. Right, I'm going to work it like this so that it gives us a better workspace or understanding. Right, the first thing I have is something called a scalar. Right? When we talk about a scalar, we talk about any measurements, of a physical quantity which only has magnitude. Right? So what we mean when we say magnitude is that I'm talking about it has a size. Right? For example, things like mass, right? Or distance or length, time as well. Height, right? Even speed. Right. So when I'm looking at these, I would consider these to be scalar quantities, or the idea of something being scalar. So when I'm talking about something being scalar, is that it only has a size. So if I want my mass, I can look on a scale. The distance, I can use a measuring tape. Length, I can use a ruler. Time, I can use a clock. Height, I can use a ruler. Speed, I can use a speedometer. It only has a size. So I know that mass is going to be in kilograms. Distance is always in meters. Length is always in centimeters. Time is in seconds. Height, always in centimeters. Speed is in meters per second. All right, so what I'm looking at here is the SI units over there. All right. So I want you to think about it like this. Often we compare two things. We look at things like mass versus weight. Now people will say, what's your weight? But what they should be asking you is what's your mass? Because when I'm looking at my mass is in kilograms. That's what they want. My weight is measured in newtons, which is my mass multiplied by 9.8 meters per second, which is called the gravitational acceleration. Right. So people will often say to you, what's your weight? But that's the wrong question, because look here. Let's say I get onto the scale and I weigh 65 kilograms. Right? Then someone asks me for my weight. My weight is actually 65 kilograms multiplied by 9.8. And what's 65 multiplied by 9.8? It's 637 newtons. That's my weight. This is my mass. Now this mass value here, this is what we call a scalar, because it only has size. But this here, which is weight is what we call a vector. And a vector, let me go here, let's have a look at what a vector is. A vector, right? A vector is a physical quantity that has both magnitude and direction. That's the important part, which means it has a size, size, and it has some sort of direction. What we mean by that is, if I look here at your mass, I can say you weigh 65 kilograms, but in which direction? There's no direction, right? So that's what we call a scalar quantity. It has no direction. It's just a basic measurement that only has magnitude. A vector has to have that direction. So a couple of things that I would consider as vectors is force, acceleration, or deceleration. I can even say deceleration. I can look at weight. I can look at something called displacement. I can look at velocity. Right, those are my different types of. So for force, I can look at your weight. I can look at how hard you, I'm looking at push or pull. Remember, with acceleration, how fast am I going? What about deceleration? That's acceleration, but in the opposite direction, which means to slow down. So if I look here, force is measured in, let's undo that, newtons. Right? Acceleration and deceleration in meters per second squared. Weight, we know, is in newtons. Don't forget that's an N. Displacement is measured in meters. and velocity is measured in meters per second. Now, what you would notice now is a bit of a link. Let's have a look here. I've got displacement here, and I've got distance there, but look at the SI units. They're the same. I've got speed here, and I've got velocity. Look at the SI units. They're exactly the same. The difference between the two is that the one just has magnitude or size, but the other one, when we use it, has some sort of direction, right? So when we talk about vectors and scalars, we're looking at units of measurement or ways in which we can measure things. And if I can measure things, I need to be able to understand, does that thing that I'm measuring need a direction, or is it okay with that sort of situation? So when I look at scalars, I want only the magnitude or the size of it. But when I look at vectors, I want the magnitude, and I want, which is the size, right? That size is always a numerical value, or I want the direction, right? So those are my two. So like I said, we're going to look at distance and displacement and speed and velocity in quite a bit of detail, as well as acceleration and deceleration. All right, let's have a look at the next thing. The next thing I want to look at is distance versus displacement. Right. What do we mean by the two? Let's say I go to a theme park. Let's do that. Say I go to a theme park, and I'm going to go on the roller coaster. So I'm going on the roller coaster, and there goes the roller coaster, and there goes the roller coaster. Right? So I'm in my little cart. Let's just draw a little cart here. Oops. Right, I'm in my little roller coaster here. And what I'm going to do is I'm going to follow this pathway, because that's the track of the roller coaster. Right? Going up, down, whatever the case is. Right. And I want to reach the end. That's the end of the track. So I follow this pathway, and I move through it and move through it and move through it, and I get to the end. Right? Now let's just say I have a friend of mine. And a friend of mine is going to wait for me at the end, from point A to point B. They're going to wait for me here at the end. So instead of taking the actual roller coaster, what they're going to do is they're also going to start here. So let's say you have your friend. They're starting exactly here at point A. And all they're going to do is, instead of taking the actual roller coaster, they're just going to travel all the way from where you were, all the way to B. So what they've done is from here to here. All right, so let's just have a look at the two routes that you've taken. The route that you're taking is in blue, so that's you. And over here in the yellow is your friend. Right? And they're going to meet you at the end. So what I mean by distance, right? Your distance is what I would call a physical length, right? So a physical length means it is dependent on a pathway. There must be a pathway to get there, right? If I look here at your friend, what your friend is doing is something called displacement. If I displace something, it means I'm going to, it's the shortest distance between 2 points. Right? So it's not dependent on a pathway. Right? It's always from the starting point, it's a direct route between 2 points. So let's have a look at what we mean by that. Let's say you live here, and over here is Johannesburg City. Right? You live here, and this is the city with its skyscrapers and whatever. Right? Right, there's the city. Right. For you to get in the city, you're gonna leave your house. Right, you're gonna leave your house, go up the road, down the road, take a U. Here we go. Then you're gonna get onto the highway and you're gonna go all the way to the city. You're gonna get into the city. So you went from your house to the city. Right. Now, let's say you got yourself a helicopter. Now I don't have to take my car anymore. I can just drive from here to the city. So, or fly rather. So I'm going to start at home and I'm going to go straight to the city. Have a look at that. So I've gone from home straight to the city. And when I look at the difference here, the direct path that I went with the yellow line, that would be considered the displacement. Right? And what I did with the car, right? The car is I did a distance. Right? Did I go from home to the city for both trips? Yes. Did I take 2 different pathways? Yes. The one pathway was dependent on the roads and the traffic and so on, and the other pathway was a direct pathway between home, which is there, and the city, which is over there. So that is the difference between distance and displacement. However, distance is measured in meters and displacement is always in meters. Both of them in meters, the little m. Right? How we represent them though is different. Distance has a symbol of capital letter D, and displacement has a symbol of a triangle and an X. We call that delta X. So a triangle, right? A triangle means delta. It's a Greek letter and it means change. So think about that. That's the symbol. And X here stands for position. Like when you do a treasure map, X is where the treasure is. It's the position. So delta X means the change in position. So displacement is the change in position. So if we think about that, the roller coaster, he started off here at A and he ended up here at B. Start point, end point. The change in position. I was here and now I'm there. Alright, so we're going to look at that in a little bit more detail. Alright, the next little topic we're looking at is how do we represent vectors. So we can do 2 things. The first thing we can do is calculations. Alright, that means we have to do some sort of operation. The other one is we can do a vector diagram. Now, these are very, very important, especially for grade 10, 11, and 12. You need to know how to do a vector diagram. But there are rules, right? Drawing vectors, right? Or rather, we look at the representation of vectors. The first thing is a vector is drawn as a straight arrow, right? If I'm looking at a vector that is drawn as a straight arrow, there are different things that that vector will represent. So if I had to look at a picture of a vector, 1 second. Right, this is what a vector would look like. And like I said, a vector is drawn as a straight arrow. And let's see what we mean by what's happening on this arrow. Right, the first thing, if you have a look here, it says magnitude. That means that if I have an arrow, right, the length of the arrow must represent the vector quantity, right? So what we mean by that is, let's say I had a force of 12 newtons and they said to draw a vector. So when I draw the arrow, it must be to scale. So before I even start, I must have a scale. So I'm going to say 1 centimeter is to 1 newton. So my vector should be 12 centimeters if I'm representing a 12 newton vector. Just make this a bit smaller. So when I draw it out, I'll measure 12 centimeters and I'll represent it with a head. So can we see here a head? The head must be in the direction of the vector. So let's say that this vector is moving to the right. Right, so the vector itself will be 12 centimeters, but when I label it, I'm going to say the force, is equal to 12 newtons. Now, this little symbol here that you can see, it's a, undo that, that's what we call a half arrow. A half arrow must be drawn like that. It must be put over the symbols of all vector quantities. Please let me stress this, if you don't put it over a vector quantity, it is a possibility that you will get a -1 for your question, right? For example, if I said weight, what's the symbol for weight? If I had weight, which is W, then I must write it as W like that. Let's say I had acceleration. The symbol is little a, but it must be written like that. Oops. Right? So, like we were saying, the length of the arrow must represent the vector quantity. There must be a scale. Your scale can even be 1 centimeter is to 10 newtons, or 1 centimeter is to 100 newtons, or 1 centimeter is to 50 newtons. Any type of scale. But it always, we start with centimeters to newtons. So, I know that the head of the thing must be an arrowhead, and that must point in the direction of the vector. So to the left, to the right, we're going to talk about that now. The end here is called the tail, right? The tail, we're going to do some diagrams, and the size and length will tell me what's being represented. Remember, I can always have even 1 kilometer is 1 centimeter represents 50 meters. I can have even 2 centimeters represents 1,000 meters per second. Right? Whatever your scale is, it's up to you for that sort of thing. Right. Please make sure you need to show with these arrows magnitude and direction. There's the magnitude, that's the size of the actual arrow. Direction comes from the arrowhead. So that is how we represent all vectors. Couple of other things. Number 3. All vectors must be drawn with a ruler and pencil. Very, very important. You don't use a ruler, you don't use a pencil, we don't even mark it. So please make sure that when you are drawing your vectors, you must use rulers and pencils. Right, let's have a look at the next thing. Before we go to the next section, let's just have a look here at something called vector notation. So remember when we said vectors are different from scalars? I touched on this a little bit, but here's a little bit of notes. So what we're going to use is we're going to use the symbols and we're going to put arrows at the top. We usually use what we call a half arrow. Alright, so if I don't put an arrow, it only represents the magnitude. If I do put an arrow, it's telling me that there is a vector. So things like, and I'm looking here, things like force, weight, velocity, all are vectors, right? Meaning that they must have magnitude and direction, and they must be represented with these half arrows. So please make sure you have your vector notation when we're working with these vector diagrams and so on. All right, when we look at a direction, let's have a look here at direction. All right, we have to talk about different types of directions that we can or cannot have. So when I want to show directions, there are different ways. So when we talk about general directions, we're looking at these types of directions. So here I would be going to the right, or I can even say forward, right? Here the direction would be upward, this direction would be downwards, and then this direction would be left or backwards. I can even say that forwards, I can say it's going towards, and backwards I can even say away, right? That's the first type of direction. The second type of direction, please make sure you get these drawings into your books. They all mean a different thing. Right, the second type of direction that we get, just move this out of the way, come back to that, is we're looking at something called compass directions. Right, when we talk about compass directions, all we're saying is to the, let's say for this one, to the east. You can say southwards, right? You can say in the direction northeast, right? So when you talk about compass directions, you can use them for what they are. You know that it goes north, east, south, and west. What's important about these directions is that we need to understand that when we use these directions, we must use the directions given in the question. So if they're using the words like downwards, then you can't use the answer as southwards. So you need to be relevant to your question, but you need to be prepared to work with compass directions, or you need to be working with compass directions or normal directions, but work within relevance. Right, the next thing we're looking at is, that's compass directions. The next one that we're looking at is a little bit more complicated. This is called bearing, right? When we talk about bearing, we need to make sure we use a protractor. This little instrument that you get, if you don't know what a protractor is, this instrument that you get in your math set, right? It is used to measure degrees. Right, now when we look at something like this, we're going to start here at north with 0 degrees. So there's where the starting line is. Can we see that? And let's say they want a bearing of 45 degrees. Right? So I'm going to take my protractor, and let's use another color, darker blue. Right, I'm going to take my protractor, I'm going to place it here in the center, right, and I'm going to measure a bearing of 45 degrees. So I've got a bearing there. So the angle that's between here and here is 45 degrees. So I can say that if I wanted a bearing of 45 degrees, I can either say it has a bearing of 45 degrees, or I can say I'm 45 degrees, whoops. I can say I'm 45 degrees east of north. So how that reads is 45 degrees east of north. Right, does that make sense? Right, so let's say another example. Let's say, for example, they said they want a bearing of, they want a bearing of 260 degrees. So let's have a look at that. So if I start here, can you see it's 0? So remember, when we work with bearing, you must start at 0 at north, and you must move clockwise. So I've got here moving 90, 180, 225, 260, 260 degrees. Right. So when I'm drawing something like that, it's going to look like this. Right. So this is what it looks like if I had to draw it out. From 0 degrees here, from 0 degrees there, there's 90 degrees, 180 degrees, 270 degrees, and we're back here at 360 degrees. So I go all the way around and I end up there. So either I can say it's a bearing of 20 degrees, or I can say I measure from the other direction. So let's say I measure from here to there, which is left with 10 degrees. So the 260 or 10, and if it's the 10 degree, I can say 10 degrees south, I'm going towards the south of west. So how we notate that is, there are two notations. You give the degrees, right? And then where you're going to where you're from. All right, so that's how we work out bearing. So remember, bearing works from using the same points as a compass, but you're going from north all the way around in a clockwise direction. All right, so when I draw this vector out, let's just have a look here. Let's say I did draw and I had this north, east, south and west. And let's say I want 40 degrees and 2 kilometers, right? So I'm going to say 1 centimeter is to 1 kilometer. So I'll measure with the protractor 40 degrees is here somewhere. Oops. And then I'll make this line here represents, so it will be 40 degrees there. And this line here is 2 centimeters long and will represent 2 kilometers. So bearing, remember, you're moving in a clockwise direction. Right, and that's how we work with direction. What I could also look at when we talk about this sort of thing is I can look at different types of bearing. So let's have a look here. Can you see each of these bearings? They start at the point north. The other cardinal points are here. There's one there, there's there. That's south, east, west. South, east, and west. That's east, that's south, that's west. So if I had a bearing of 34 degrees, I'm measuring from north to 34. 133 from north down. Bearing of 300 degrees, come all the way from north, all the way around. Right? If I was measuring this angle here, it would be 60 degrees. And then remember where I'm going, west of, and where I'm coming from, north. That's how it will be labeled, the back end of it. So please make sure you understand these types of notations as well. All right, let's go to the next thing. Right, if I look at the resultant vector, I can say that the resultant vector is the sum of 2 or more vectors. It is the result of adding 2 or more vectors together. So I can say that the resultant vector, right, so R like that, the resultant vector, oops, is a single vector whose effect is the same as the individual vectors acting together. Alright, so if we're having a look here, it says that if I had vectors A, B, and C, so if I had, let's say, for example, vector A at a bearing of 260 degrees, vector B at a bearing of 135 degrees, and vector C at a bearing of 45 degrees. Alright, so if I'm looking at something like this, let's just say we had Joe over here, and Joe was going to get up and he was going to take a walk. He was going to start at point A, so let's have a look here, and let's say he was going to walk 4 kilometers, and then he was going to walk 6 kilometers, and then he was going to walk another 7.5 kilometers. All right, so the first thing we have a look at, we can say that 1 centimeter is to 1 kilometer. Right, that helps us a little bit because that's going to give us an idea of how we're going to draw these 3 vectors. So when it starts, I'm going to put a dot here, and I'm going to say that this is Joe, and he starts here, and I'm going to draw a little Cartesian plane at point A. He's walking at a bearing of 260 degrees, so I'm going to measure from here to here, and I'm going to get about 260 degrees. So what I'm actually bringing in here, and I want this whole thing, he's going to be moving at 4 kilometers, so I need it to be at least about 4 centimeters. Right, I've got that vector sorted out. Right, then he walks here to point B. So vector A here was a total of 4 kilometers. Right, at vector B over here, I'll draw a little Cartesian plane. At vector B, he's going to go 6 kilometers at 135 degrees. So 135 degrees going from north bearing is about there. And he walks a total of 6 kilometers. So we'll take our rulers and we'll measure from here to here at least 6 kilometers. Right, so then I've got the second one at 6 kilometers. Right, so that's the first one, arrow, second one. Then at point C it goes 7.5 degrees. Draw a little Cartesian plane here. And he's going to go at 45 degrees, which is around this point over here, about there somewhere. So I'll bring in my ruler. And let me just reduce this. And I'm going to go 7.5 kilometers. Right, so I'm going to move here. Oops. I'm going to come in 7.5 kilometers. Sorry. All the way there. Right, and that's the end point. So now what I'm looking at is, this here took 7.5 kilometers. So he went from this point and he walked 4 kilometers plus 6 kilometers plus 7.5 kilometers. Right, that's going to give me 17.5 kilometers. 17.5 kilometers. That's how far he walked. When what he could have done is actually, instead of doing all of that, he could have just walked straight from here to here. So now, what we call that, this here is the resultant vector, or we can call it F, or rather, the resultant vector. Because instead of walking all this way just to get to this point here, point X here, he could have just went directly from A to point X. So when we talk about, if it says if displacement vectors A, B, and C are added together, so A plus B plus C, they should give you the vector R. So vectors A plus B plus C should give you vector R. So this value here should be 17.5 kilometers when we measure it out, if we've drawn it accurately. Alright, so vector R is determined by using, we can use, it's called an accurately drawn scaled vector addition diagram. So we're going to look at vector addition, but what we're looking at is, if I had to take a bunch of vectors and put them together and I look at how they interact with one another, I have to look at how they function with each other. And when I'm looking at how they function with each other and I add them together, so remember here, if I'm looking here, it says the sum. If I'm going to add these vectors together, whatever I get at the end is called my resultant vector, which means I could have actually just walked from point A to point X without having to go through this whole other pathway. Please make sure you get this into your books. The next thing we're looking at here is something called the vector equilibriant, or we can say it's called the vector equilibrium. Now, you're not going to see it often, but when you do see it, what you need to understand is that the equilibriant is the vector which has the same magnitude but opposite direction to the resultant vector. And so if I'm looking here at these two concepts, right? The first one over here, picture number A here, and then picture B. If I look at picture B, I've got 500 newtons and 450 newtons. So these people are pulling over here with 500 newtons, and the other people are pulling on the other side with 450 newtons. So if I had to look at these two, the couple on the left-hand side versus the couple on the right-hand side, I know that who's going to win is the couple that's pulling with a bigger force. However, when I have two equal forces, so if I have a look here at this one, I've got 500 newtons and they're pulling this one left and 500 newtons here, and this one's moving right. Right? When they're equal, so can you see they're equal to each other, but they're moving in the opposite directions, we can say that if I see this situation, it is in equilibrium. So basically it's a vector that when we add it to the system, we actually end up cancelling out. So technically, if I'm pulling to the left and this person's pulling to the right, and we're pulling with the exact same forces, those forces are going to end up cancelling each other out. It's the same as the resultant, but in the opposite direction. If they cancel out each other, if something is in equilibrium, we say there is no movement. If there's no movement, we can say that the resultant force, the Fr, is equal to 0 newtons. That means it's not moving left and it's not going to move to the right. So not left or right. So we can say therefore the system is stationary. Right? Stationary means it's at rest. At rest means there is no movement. So the only way that that can happen in that situation is if you have all of the forces that are acting on the object. So in this instance, that's the object. All the forces acting on that object are equal, but in the opposite direction. And then you reach something called equilibrium, or we reach the equilibriant of the situation. Now let's have a look at the next thing. Now let's have a look at the idea of vector addition. Right, when we do a vector addition, what we have to do is we have to add vectors. Alright, so if I want the resultant vector, I must add vector 1 plus vector 2 plus vector 3. So if I'm dealing with force, then I can say Fr, which is a force, is equal to F1 plus F2 plus F3. If I'm working with acceleration, then I can say that AR, which is the resultant of acceleration, is equal to A1 plus A2 plus A3. Right? That's how you write those formulas out. But have a look here. The only thing that we have is plus. So what happens if all the forces are not in the same direction? So let's do this. The next thing that needs to happen when you do any vector calculations. So we have vector calculations. Right. Remember we talked about the first one being graphically. We're going to get to that now. And the second one is algebraically. Right. Now, when we do any types of calculations, the first thing you need to do is we need to find what we call a positive direction. Right. So if I'm looking at a sum and it says that Joe walks east to school, when he comes back to school, he has to work west. Right, so when we talk about a positive direction, what we have to do is we have to choose a direction that is considered to be positive. That means if anything goes, and what we call that is we say it's going in the direction of motion. In the direction of motion means it's doing what is natural. Right? So I can say at the beginning of any of these calculations, I can say let east be positive. Or I can say let south be positive. Let right be positive. This here, you decide. Right? Now, in these instances, if I said that east is positive, that means that naturally west is negative. So this helps me because if west is negative, that means when I do these vector additions, I'm going to have negative values. If I said let south be positive, then north is negative. Right? So whatever you decide that will be positive, the opposite of that will be negative. So when we're doing any of these vector additions, you need to start thinking about what would you consider as being a positive direction or a negative direction. Right? Everything else will follow after that. So if I look here, let's look at these. The question that they're going to ask us for something like this is they're going to say, calculate the net force or the total, or the resultant force. Right. So here I've got things moving either to the right or to the left. So I'm going to say I'm going to take anything that moves to the right as positive. I'm going to make that statement. All right, so let's have a look at the first one. So these are all forces. And let's look at the first one. The first one, it has an 8 Newton force moving to the right and a 2 Newton force moving to the left. Now I'm taking, every time I see a right, something moving to the right, it must be positive. So I'm going to say, let's number this 1, question 2, question 3, question 4. All right, question 1, I'm going to say FR, which is the net, is equal to F1 plus F2. Right. So if I put it here, my F1, I'm going to say is 8 newtons plus my F2. Because this is moving to the right, it must always be positive when I substitute it in. This one's moving to the left, so it's going to be negative. 8 plus minus 2. And 8 plus minus 2 is 8 minus 2, which is 6 newtons, which is FR. And if I had to graphically show it, let's say, for example, that this whole thing was 1 centimeter is to 1 newton. And I had to draw it out. Then what I would draw here, is a vector. The length of the vector is going to be 6 centimeters. But the label is going to be FR is equal to 6 newtons. Right. Now, if the FR is equal to 6 newtons, what's important for me to understand is because the answer is positive, I must, and the answer is positive, and the answer is a vector, I must have a direction. All right, so when I write my final answer out, I must say, therefore, the resultant force is equal to 6 newtons, and because it's positive, it's related to the right, isn't it? And because it's a vector, it must have this direction. So 6 newtons to the right, or you can say in the direction of motion. Right. Let's look at question 2. So this one's question 1. Question 2. Here I've got 10 newtons moving to the right, and I've got 2 newtons moving to the right. So both of these values are positive. So if I say Fr is equal to F1 plus F2, I must say 10 plus 2 is going to give me 12 newtons, and the value is positive. Remember what we said? Anything that's positive is to the right. We say to the right. So therefore, Fr is 12 newtons to the right. Right, let's have a look at the next one. Question 3. Please make sure you write down these questions. Right, question C, or question 3 rather, they've given me 8 newtons to the right, and they've given me 8 newtons to the left. Right, so I've got a positive here and a minus, and the magnitudes are both 8. So I'm going to say Fr is equal to F1 plus F2, which is equal to 8 plus minus 8 is going to give me 0 newtons. And the only time that that's going to happen is we can say the 0 newtons, the reason is no force on the object, which means, therefore the object is in, and remember we discussed this, equilibrium, because the forces to the right and the forces to the left are equal. And let's look at number 4. Number 4 is a bit different. Just going to do it in another color. Right, number 4. For number 4, I've got 5 newtons to the right, which is going to be positive. I've got 3 newtons to the right, which is also going to be positive. And I've got 10 newtons to the left, which is also positive. Right, so let's do this. We're going to say Fr is equal to F1 plus F2 plus F3. And here I've got 5 plus 3 plus negative 10. And I'm going to pop all of that into my calculator, and I'm going to end up with negative 2 newtons. Right. Now, this is important. I cannot leave my answer as a negative. So I must make a note. No negative answers. What I have to do is, I must change it to positive, and then I must add in the direction. Because what's actually happening here is I've got this 5 here and this 3, and they're pulling, but there's a bigger force here, the 10. So is this object going to move to the right or to the left? Because the 10 is more than the 5 and the 3. So what's going to happen is I must say therefore, so underneath here I would say Fr is equal to 2 newtons to the left, or I can say in the opposite direction of motion. I can say in either one of those. So remember, when you get a negative answer, you cannot leave it in a negative form. you must change it to positive. And when we add in the direction will make sense. So please, this is very, very important. All vector quantities must be positive, because it's the direction here that's going to help me to see that that number was a negative. So when you do these types of calculations, right, we're going to use vector addition like this. A nice way of thinking about something like this is, if I want the net force, I can say F net, or let's do this. I can say the resultant force is equal to the forward forces, whatever I consider forward, minus all the backward. Or I can say that the resultant force is equal to F1 plus F2 dot dot dot. Right, you can think about it in these two ways. These are two formulas. Obviously they're not on your formula sheet, but it's a way of thinking about how do I add and subtract, or how do I work with vectors. Right, so this is the work that we're looking at. And these are the types of formulas that we're working on. This here means the same thing. Right, resultant force, resultant velocity, whatever the case is. Now let's look at some examples. Now, this method that we just did, I want you to make a note for yourself. This is how we function with algebra. Right? It's the algebraic way, or the mathematical way of finding the resultant force. Alright, so if I had to do the other one says, oops. Oh, no, it doesn't. It does. So we have it algebraically, or we can use graphically. Right. When we have graphically, we must use the rules for drawing vectors. The rules for drawing vectors. For the method we're going to use is called the head to tail method. Right? It's called head to tail. Remember the rules. Don't forget the rules. We're going to need arrows with arrowheads. We're going to use pencils and rulers. We need pencil plus a ruler. We need a proper scale. We need arrows. Oops. Right? Those are all the prerequisites of how to draw this. Let's have a look at the head to tail method. Right, the first thing we look at is we're looking at the head to tail method of vector addition. Right, the first thing they're telling us that we need to do is you need to draw a rough sketch. Right, a rough sketch, what it looks like is, if I'm thinking of a rough sketch, it's like Joe walked to school, then he went to the shops, and then he walked back home, great, and then he went to the mall. All right, this is what I'm drawing here. So home, school, shops, home, mall. All right, that was his whole situation. We start off with a rough sketch because it helps us to see a little bit better. Right, the next thing you need to do is you need to choose a scale. Remember we spoke about the scale? The scale is from centimeters, right, to another vector, which could be kilometers, it could be velocity, could be kilometers, could be velocity, could be another type of force, whatever the case is. Right, the next thing it says choose any of the vectors and draw it as an arrow in the correct direction and the correct length. Right, so choose any of the vectors and we're going to draw them with the correct length. The correct length is according to the scale. Right, so what we meant by that is the first thing they want you to draw is they want you to actually draw a vector. Right, so let's say that's the vector. The vector is 8 newtons. Done. The next thing says take the next vector. So let's say there's 3 vectors. The next vector and draw it as an arrow starting from the arrowhead of the thing. So I must go to the head here and put the tail of the next vector, and let's say that's 4 newtons. Then I take the next vector and I put it at the head here and I make that, let's say, 6 newtons. So can you see why it is called a head to tail? Right, so from the first vector in the correct direction with the correct length. Remember, all of these values have to be with our scale. Right, so you have to continue and continue until you have drawn each vector, each time starting from the head of the previous vector. This way the vectors can be drawn one after the other in what we call a head to tail. Right, the last thing here that we're looking at is the resultant vector must be drawn from the tail of the first vector to the head of the last. The head of the last. Right? Its magnitude can be determined by the length of the arrow. Because remember, if I had a scale of centimeters to newtons, if I measure the centimeters, I should know how many newtons. And its direction can be using from a scale diagram. We can use a protractor. I'm going to show you guys how to do that for the head to tail method for the vector diagrams. Alright, so that's the type of method. I'm going to do some examples with you now, and we can see how we draw these vector diagrams. Please make sure you get these rules written down though. Alright, let's have a look here. Alright, it says, for example 1, a car breaks down on the road and you and your friend who happen to be walking past help the driver to push start it. Please make sure you write down the question before you start. You and your friend start together at the rear of the car. So rear means back. If you push with a force of 15 newtons and your friend pushes with a force of 45 newtons, what is the resultant force on the car? Use the head to tail technique to calculate graphically. Alright, so the first thing I need, if I look at my rules, I need a rough sketch. So a rough sketch just means if this is the car, right, you are over here and you pushing, and your friend is over here. Oops, friend had no neck there. Your friend is over here and they're pushing, and you both are pushing in that direction. So you at the rear. So if I'm looking at it like this, I'm going to say that the car is going to move this way, which is going to be to the right. So I'm going to take right as positive. Right. So anything that moves to the right is positive. Anything that moves to the left is negative. So the first thing is, got your rough sketch. Please make sure that you indicate this to your marker. NB. Right? Very, very important. If I go back to the rules here, you must indicate your positive direction. You must do this. Please, very important. Right, the next thing you need is a scale. So I'm working with 50 newtons and 45 newtons. Now remember, the smaller the scale, the more accurate it is. So I'm going to use centimeters. I'm going to say 1 centimeter is to, I can either choose 5 newtons, or I can say 1 centimeter is to 10 newtons. But the problem with that is there's a 45 here. So it would be better for me to use 1 centimeter is 5 newtons. So, therefore, I've got force 1, which is equal to 50 newtons. And if I have 1 centimeter is 5 newtons, that means I'm going to have 10 centimeters. Right? My force 2 is 45 newtons. And that's going to give me 9 centimeters. Alright, so that's the first thing. The second, so we've got rough sketch, we indicated to our marker, we chose a scale, and now we have to draw it says, draw any of the vectors. So let's pick the first one, let's draw force 1. Alright, so you're going to need your ruler, and you're going to take your ruler and you're going to measure 10 centimeters. Alright, so if I was looking here, I'm going to go 10 centimeters till there. Right, and that is my first vector. And I'm going to put an arrowhead at the end. See? It says draw any vector, draw it as an arrow in the correct direction. So remember, we're moving the car to the right. The next thing it says there, the next vector. So when I've drawn this, I must label it as F1. F1 is equal to 50 newtons. Right, now I want to draw F2. Alright, so I'll go, remember you using a pencil, I'm using a color pen for this one. I'm going to go here, and it says at the end, at the head of the, it says at the head of the one vector, I must draw in the other vector. Alright, so I'm at the head here. What is happening? Let me line it up. From the head here, I must draw 9 centimeters. And that's what that looks like. And now I've got F2, which is equal to 45 newtons. Alright, now the question is asking us, what is the resultant vector? So, if I take my ruler and I measure from here to here, that vector there is my resultant vector. So if I say (50) plus 45 and I measure that, or I measure 10 centimeters plus 9 centimeters, I'm going to have a long line here in my book. Let's measure from the right zone to the right zone. I've then got graphically, oh no, what happened to my line? Sorry. I've now got a situation where this over here, this here is the full force, which is F1. See, this one here was in the positive direction. So FR is actually equal to 95 newtons. And how did I get that? I did a calculation. FR is equal to 50 newtons plus 45 newtons. And that gave me a resultant force of 95 newtons. So what I'm looking at here is this drawing here. This is what we call graphically. Right? 1, 2, 3, and 4, 5. 5 marks. Right? When we do it, the sum, and I do it algebraically, I've got FR is equal to F1 plus F2, which is a mark. Then I substitute, and then I get a mark. But what's missing here is the direction. So I can say to the right or I can say in the direction of motion. Right. So that's the two ways in which you can do something like this. I'm going to look at another example that's a little bit more intense. Please make sure you write down the question. So we're looking now at example 2. Right, let's have a look here at example 2. So let's close this a bit. Right, I've got your example 2, and it says here, use the graphical head-to-tail method to determine the resultant force on a rugby player. If two players on his team are pushing him forward with forces F1 equal to 60 newtons and F2 equal to 90 newtons, respectively, and two players from the opposing team are pushing him backwards with a force of F3 100 newtons and F4 65 newtons. Right, let's have a look here. You've got two things happening. The first thing you have is a forward force. See, they're using the word forwards. Not east, not west, not left, not right. Forwards and backwards, which means our answers must include those words when we sorting things out. Right, so first of all, I have this boy over here, this guy here, and he's being pushed, right? He's being pushed by two members of his team. Oops. Right. Oh gosh. And he's being pushed by two members of the opposition. Right. Sorry, ignore my diagrams. It's my rough sketch. Right, so let's look at the different forces. From his team, he's got two. The 60 newtons and the 90 newtons. And from the opposing team, he's got 100 newtons. Oh gosh, what am I doing? He's got 100 newtons and he's got 65 newtons. Right, that's your information. So let's just get that written down. So on this side, we're going to take forward as positive. Anything that moves forward is a positive value. Alright, so the first thing I've got here is F1 is equal to 60 newtons and F2 is equal to 90 newtons. Right, the other one is going, so these ones are pushing this way. The other ones are coming this way. I've got F3 here, which is equal to 100 newtons, and F4, which is equal to 65 newtons. Right, those are my values, and that is what's happening in my situation. I've got here on this side all the backward values, and I've got on this side all the forward values. Right, now we've got back and forward. The diagram that we do is going to be a little bit different. Right, the first thing is I need a scale. Right, this time, even though I have the 65, it's fine. It's better for me to use 1 centimeter is to 10 newtons. Scale is done. Remember, you're going to need a ruler and so on and so on. So let's have a look here and how we're going to sort this thing out. Right, the first thing you're going to do is, with your pencil, I'm going to do it in 2 colors. You can do it for now in 2 colors, but please in the future know that you can't do it that way. Right, the first force I'm going to put in is force 1. So F1 is 6 centimeters. So 1, 2, oops, let's just go back. 1, 2, 3, 4, 5, 6. All right, that's the first one. Let's do this. Okay. So I'm going to go and put an arrowhead there. And I'm going to say that this is F1, which is equal to 60 newtons. So remember, if it's 60 newtons, it's 6 centimeters. If it's 90 newtons, it's 9 centimeters. If it's 65 newtons, it's 6.5 centimeters. Guys, this has to be accurate, because I will actually take a ruler and I will measure if you are being accurate according to your scale. So please don't pull a wool over my eyes. All right, the next one is 10 centimeters. All right, that's the one. That's F1. Then I had to draw in F2. Same stint. Remember, we're doing a head to tail. So I'm going to go back there. And from the head here, from the head of this one, I'm going to go all the way. Oops. Don't do that. I'm going to measure here. I need to go how many? 9. 1, 2, 3, 4, 5, 6, 7, 9. Right, I've got 9 there. And I can put an arrowhead there. And I can say that F2 is equal to 90 newtons. Great. Right, here's where the kicker happens. This is now at this point, right? The boy, he is sitting, now that his team has been pushing him, he's sitting over here. But what's happening at exactly the same moment, he's being pushed by the other team. So what I'm seeing in the red and blue now, that's his team. So what we do is we draw a dotted area. 2, 3, 4, 5, 6. And we're going to draw the forces that are going in the opposite direction. Because these two forces I'm seeing here are going forward. Right, now I need the backward forces. Right, the first one I'm looking at is the 100 newtons. So I'm going to go here, get my ruler, and I'm going to go here to this point, and I'm going to draw in 100 newtons. So I'm going to go 1, 2, 3, 4, 5. What's happening? 7, 8, 9, and just a bit more. Come on. 10. So 1, 2, 3, 4, 6, 7, 8, 9, 10. Right, so I've done 10 now. You see that? And I put an arrowhead there. So this means this is F3, which is 100 newtons. Right. The next thing you have to draw in is F4. And F4 is your 6.5 centimeter one. So I'm going to go here and I'm going to go 1, 2, 3, 4, 5, 6.5. Right. Yes. Oops, a little bit more. There we go. Right, and now I've got my vector diagram. So I go here, and this is F4, which is equal to 65 newtons. Alright, but this is not the end, because the question is asking you, which way will he move? Forwards or backwards? Right? Now, your F rays. Remember what they say. When we draw the F rays, it must be from the tail of the first vector, to the head of the last. Right, tail of the first, head of the last. Right, let's have a look at how that's going to look now. Right, so I'm going to go, choosing a different color this time. Say I use yellow. Right, if I look here at this green one, that's where the line at which, and you'll draw this line in, the line at which my head of my last vector was drawn. But they're saying that we must draw it from the tail of the first vector. So we're going to look here at this red vector over here. And we're going to draw it to that yellow line over here. Right, so let's see what that looks like. And what I've got here is when I measure it with my pen, my ruler, I'm actually going to get, for this yellow line, I'm going to get 1.5 centimeters. And that 1.5 centimeters, according to our scale, is actually 15 newtons. So on my diagram, when I label it, I'm going to say FR is equal to 15 newtons. And look at the direction in which it's moving in. It's moving to the left. So I must say, therefore, the F res, or the resultant force, so I can write this, please just make a note here. I can say FR, or I can even call it, remember what I said? F res. That means resultant force. Alright, so I can say therefore the FR, or the resultant force, is equal to 15 newtons. And look at the direction of your vector. It's moving to the left. But even though it is moving to the left, remember the words that we must use. It's 15 newtons. We know it's going to the left, but in this question, they're using the words forward and backward. So forward is positive, and if I look here, it's not moving forward, it's moving. So it's 15 newtons backwards. Right, and that's how you answer the final question. So please make sure that when you draw, you are accurate in your centimeters, accurate in your labeling. Make sure you keep your vectors going in the forward direction and in the backward direction a little bit apart, so that we can see that there's a difference between those things. Remember, the better the scale, the better the diagram. All right, let's have a look at the next thing. This whole thing was a head to tail, graphically. Now we're going to look at algebraically. So if I'm looking at this whole situation in a way of algebra, we decided that anything that moves towards something is positive, and anything that moves away would be negative. That means that we decided that F1 and F2 are both going to be positive, and F3 and F4 are going to be negative values. So this tells me that it's moving forward. This means it's moving back. So let's do your sum. So we're going to say FR is equal to F1 plus F2 plus F3 plus F4. F1 we know is 60 newtons. Oops. Plus F2, which was 90 newtons. Plus F3, but F3 is backwards. So F3 is going to be plus minus 100 newtons. Plus, and F4 is also negative because it was moving backwards, plus minus 65 newtons. All right, and if I pop all of that into my calculator, I'm going to get a value here of negative 15 newtons. But remember what I said, you can't have a negative answer. So the rule is make it positive. Great. FR is equal to 15 newtons. And you have to put in a direction. And this one, because it's negative, we know anything that is negative is backwards. 15 newtons backwards. Right? Or you can even say in the opposite direction of motion. Right. So for all vectors, remember, answers are in positive. You may not leave answers in negative. So we take away the negative and then we make it a positive, and that brings us to the end. So the next thing we're going to look at is motion in one dimension, still part of kinematics, but the next video, so next up is kinematics 2. Please check out the video.